Okay, let's see how do you use the linear regression, how do you estimate and interpret the linear regression in R. And let me be clear, we don't have the space in this lecture and this class to teach you everything that you need to do in order to be certain that the linear regression worked appropriately. So there are many diagnostics that you need to conduct in order to see if your model is, at least statistically speaking, correct. But we don't have time for that right now. So let's focus on how to use the function and interpret the results in terms of what we learned in this lecture. Okay? The preliminary steps is that you need to install and load two new packages, JTools and Huxtable, I guess is the name of that package. And you need to also load DS Labs and Tidyverse and load the dataset Gapminder that is attached to the package DS Lab. We're gonna transform two variables. One is gonna be the log of GDP. So we're gonna use the GDP has a problem, and there is a lot of variation in the potential GDPs of the countries in the world, right? So you can have countries with very small GDPs and countries with very large GDPs, such as China, the US, and India, I don't know. So that creates a lot of variation, and that brings problem to estimation. For that reason, you use the log when you want to control or transform the variable in a way that is more appropriate to conduct this kind of linear regression, okay? And the other variable that we're gonna create is actually the region Northern Africa. So basically, we want to see, we create this dummy variable, Northern Africa, if a country belongs to that region. What is the background? So we want to explain life expectancy, in a cross-national setting for the period of from 1960 to 2016. And we claim that the GDP of a country is related to the mean life expectancy in such a country. And we want to control 4 countries from Northern Africa because these countries experience huge problems that can decrease the life expectancy. And these factors are not necessarily related with the GDP, such as internal wars, pandemics, famine, and other kind of problems. So our hypothesis is countries with higher economic development tend to have higher means levels of life expectancy than their less affluent counterparts. This is the model. So look at the function. The function is, you need to use this function LM. LM is part of the package, the basic packages of R. So you don't need to download any additional package to use this function. And you need to create a new object called model1 in this case, but you can call it as whatever you want because we want to save the results in that object. And we're going to use that object to do, for instance, post estimations, to run diagnostic tests, to plot figures, so to create tables of summary of results. For that reason, you need to create this model, this object called model. What else is important to say here? It is important to notice here that the function mimics the formula of the linear regression, okay? So in the left side of the tilde, in this case, you have the dependent variable, which is life expectancy. And in the right side of the tilde, you have all the explanatory variables. And actually, those explanatory variables are separated by the plus sign. Like emulated that you are saying this, you're going to add all those individual effects, okay? And the other thing is that you need to tell R what is the data that you're using. Simple like that. In order to see the results, you need to use this function summary model1. If you just run model1, you're gonna see very limited information. You need to use summary model1. And you see this kind of table, okay? We don't have time here to explain you how to transform this table into a more beautiful publishable table. It doesn't matter right now. The most important thing is to see how can we interpret these results. Okay, the first thing that I want you to notice is that you have here your log GDP, so this is your independent variable, and you see the t-value of that, of the, in this case, the beta sub 1, or the effect of log GDP on life expectancy. And you can see that t-value has a very large value, right? It's 52. And remember that when there is a normal distribution, in this case you have 7,000 degrees of freedom, so it's a very large sample. It's probably similar to a normal distribution. So only with 2 or with a value higher than 2 t-values, you should have a statistically significant result. But you have here 52, so you're totally fine. Okay. And now let's see the p-value. And the p-value here is very tiny. Remember, this E16 means 16 zeros after the decimal point. And for that reason, you see the 3 stars. Okay? You're fine. You have the stars. Great. Okay, so the results are statistically significant. Now let's see the results. So this is the effect. This estimate is the effect of log GDP in your variable of interest. Something that is important to highlight here is that the sign of the effect is positive, as we expected. It could be negative, right? But in this case it was positive, which is great. So you have a statistically significant hypothesis or relationship, and you have support to your hypothesis. Okay? The sign of the effect is correct. Okay, how do you interpret this? Basically, you are saying that an increase in 1 unit of the log GDP is related to an increase of 2.3 years in life expectancy. So a country that is 1 unit of the log GDP is, or has a 1 unit higher of the log GDP, the citizens of that country tend to, or the inhabitants of that country tend to have 2.3 years more life expectancy than a country with a 1 unit less of the log GDP. The crazy thing here is how to interpret the log GDP, but that's not relevant right now. Okay? Don't imagine that this is not log GDP, this is just GDP. Okay? If you have a country with, instead of 2 in the GDP, you have 3 GDP, that's great. So you have, I don't know, you have 2.3 years more life expectancy. This is what these results are telling you. Okay. Something that I want to highlight here. So we just saw that the results are statistically significant, but just to try to process a little bit more, to apply these ideas of the 95% confidence intervals. So remember that in order to estimate the 95% confidence intervals, what we do is that we multiply the standard errors by 2, and we add that value and subtract that value to the estimate of the, in this case, our independent variable, right? And if we have 0 within that interval of the 95 confidence intervals, we have problems. We cannot reject the null hypothesis. But in this case, you can see that there's no problem at all. Okay, so the 2 confidence boundaries will be above 0, so you're gonna be fine. But sometimes you have many variables, or you cannot easily estimate this, or you don't have time to estimate it with your calculator or something like that. So you have a function, this is confidence function, that help you to estimate the confidence intervals. So you have here, and you need to write here the level. It could be 90, but in this case it's 95, which is the standard. So you can see here that the confidence intervals are above 0, which is great. Okay, another thing that I want to teach you is how to plot the effect of x and y. So how do we expect that y is going to behave according to the effect of x? Okay, And we use this function, effect plot, from the package gplot, I guess is the name. And as usual, you create a new object called plot. You use your model. So for this reason, the model is important. And you use this command called prediction log GDP. This is very important. You can put here, if you had, for instance, a model with 10 explanatory variables, you can put here the variable that you want to see the relationship between that variable and y. So what you are saying here is R, show me the predicted value of y according to the values of x. Okay? And actually you can say, give me the intervals, the confidence intervals. Okay? And the results are something like this. This is not the most beautiful, but this is kind of, I like it. I like it. I would change the line for a red line, but this is fine. So this can help you that the results are, the relationship is positive and is statistically significant. Okay, that's nice. Okay, and the final kind of plot that I want to teach you is the forest plot. The forest plot can replace the table of summary of results, and it's very powerful to some extent because you can put all the variables, the explanatory variables of interest in just one figure. So it's great. It's a great kind of plot. Okay. So you use the function plot sums and put again the name, the model. And notice that I'm just adding a beautiful theme. Okay. And this is the result. I know this doesn't look very nice, but it's very useful and it's actually nice. It's kind of nice. So what you have here is the effect of the log GDP in the estimate. And here you see that is 2.3, something like that. And these are your confidence intervals. This is great when you have multiple variables. You don't want to see these confidence intervals overlapping with the confidence intervals of your rival explanations. Okay, and this is 0. So another thing, if your confidence intervals were crossing this 0, so your results are not statistically significant. Okay. Okay. Now let's include our control variable. Okay. It's the same, basically the same function, but you include with the plus sign your new variable, your c. Okay. The new thing here, or not a new thing, is the same thing, but you need to create a new model. Don't use the same model because you want to compare model 2 and model 1. Okay. Okay. So again, call the new object and use summary, such as in this case, use summary, and the next question is, does the result of x change after including c, or to what extent they change? And remember that the first question is, does, in this case, the log GDP is the log GDP still statistically significant when we include c? That's the first question. So if it is not statistically significant, your relationship was spurious. But in this case, the t-values are still large, the p-value is still small, so there's no spuriousness. You're fine. The first thing, you're fine. Great. So you can move to the substantive analysis. Okay, the next thing to explore is if the sign of the effect is the same. If it is not the same, there might be an interaction effect. Okay. If it is the same, there might be an additive relationship between x and c. In this case, for instance, the sign is still positive, so there are no signals of an interaction between c and x and y. Okay. And so this the effect is roughly equal. It's almost the same effect. It's 2.3. So there is an additive XYZ relationship. So you can use both the log GDP and the presence of the region of Northern Africa as explanatory variables of life expectancy. Okay? Okay, but as you learned from a previous class, in this class of descriptive statistics, we need to also explore the effect of C on Y. So we cannot just stop with the effect of X on Y if it remain statistically significant and substantially significant or substantive significant. We also need to see what happened with C. Okay? How if C also help us to explain Y, how does C explain Y? Okay? So we check here that C is statistically significant. And also we see here that it has a negative effect. So as we expected, countries from Northern Africa have 3.7 years shorter life expectancy than countries from other regions of the world. Okay, so that's the way that we use the linear regression with multivariate or with multiple variables. So we can also use this function confident to estimate the confident intervals of all your variables. And as I said, sometimes you have 10 variables, so this is very useful. You can plot the individual effects of the variables of interest. You don't need to plot the effects of all the variables that you include, only plot the effects of the variables that are significant for you, that are relevant for you for the analysis. So include, for instance, your explanatory variable, the explanatory variable of your theory, and the factors from the rival explanations. Okay? And we use the same function, and this is the result. This is very nice. Notice that this is not a confident interval. This is because you have two states of the world, 0 and 1. So all the points are or here, either here or here, okay? And this is the effect. So there is a reduction in the life expectancy of 3 points, 3 percentage points, or 3 years in this case, is years in this case. Okay, and finally, this is the forest plot of this model. It's very nice. So you can see here how the confidence intervals of Northern Africa are larger. So the result is, to some extent, we are less confident about these results than with these results. But this is also statistically significant. Okay, that's all. That's all. Thank you so much for watching this video and for your great work during the whole semester. This is a lot of information, but I hope you learn these foundations of statistics and statistical analysis in political science, and keep or return to these concepts, these ideas, and what I taught in these lectures, because it's going to be useful for your professional career, or if you want to advance in, I don't know, in graduate programs such as masters or the PhD or something like that, or the academic dimension of political science. This is going to be very useful. Thank you so much for all, and expect a technical lecture, and that's all. Bye.